My compatriot, Kumar Deepak, and my name is Michael Shaler. We're going to talk about how we accelerate graph analytics with some really, really cool hardware and some software. So by way of introduction.
So I'm Kumar Deepak. I'm fellow at AMD. I came to AMD through Xilinx acquisition. I am currently focusing on hardware acceleration of compute in general, and in particular graph analytics.
And I run our partner practice at TigerGraph, and I've done this before. I used to work with Bob Muglia downstairs. He and I were on stage last in Redmond a couple decades ago. So summary is that we are excited to be here. We're looking forward to talking to you about what we do with graph analytics at scale with extraordinary speed. So we're going to talk about how we solve real world problems. In this context, it's really important to note that this is a labeled property graph. Okay, and so we have strongly typed schemas, and we can actually leverage data that comes from RDF, but we focus on LPGs, and that's our approach. We're going to talk about how acceleration solves real-time challenges, and then we're going to dig into the technology itself and go deep. So let's dig in. So graph algorithms solve real-world problems. You know, to get here, I had to go from Boulder, Colorado to Denver to Las Vegas earlier this week, and then last night I got into New York. I caught the tram. That's all a graph, right? And so that's a graph through time and space. And what we're saying is that we can actually start to optimize for shortest path unweighted or shortest path weighted. Okay, and so what is the fastest driving route? You know, where is the best place to put a distribution center? These are all interesting challenges from a supply chain perspective, from an optimization perspective. And so we're looking to solve some real world problems. And some of those problems are very, very hard from a computational perspective. So maximal independent set is a way for routing, logistics, and other industries to actually optimize a path that gives you the fewest connections with the maximum set of vertices, which do not have edges between them. So all of a sudden, we're looking at ways to optimize for increasingly tenuous supply chains. One of our customers, Jaguar Land Rover, lost almost 358 million pounds in 2018 because they were flying blind through their supply chain, 89 days a quarter. Now they can actually reach in using graph analytics and ask what-if questions of their data, and supply chain is principally a data problem at this point, according to Harry Powell, who's our expert in that field. Summary is that we can actually solve for other interesting problems like anti-fraud. Okay, so our friends at places like JPMC and B of A do excellent work in terms of intercepting synthetic identity fraud and other kinds. And you can see that we actually use multiple algorithms to solve these problems. We use Louvain modularity, we use PageRank, we use loosely connected components, as well as diameter estimation. And you can see here's a set of personally identifiable information and applications. What happens in this world is that people generate synthetic identities, little Kumar, little Michael, little Jay, and all of a sudden they have a new identity, and then they open an account. And that's what the application part is. We are able to intercept fraudulent applications because we can actually show the lines, show the connections, to be precise, between different applications and different identities. And so we do that with Louvain, we do that with LCC and diameter estimation. So we can accelerate all these core applications, all these core algorithms using FPGAs, field programmable gate arrays. We're going to talk about that in a second. So we're able to extract features, and this is where the data science and machine learning aspects go, you know, hand in hand. You know, Jay Yu, who's our head of product and innovation, has pointed out that graph algorithms are really unsupervised machine learning at scale. And so we're talking about 40 to 100 terabytes of data that's no sampling. We're working across the whole data set and running PageRank and Louvain, which are very computationally intensive. Kumar helps us on the Louvain side in ways that are profound and provide breakthrough business value. So here are the different algorithms by use case. You know, with fraud detection, we use community detection. shortest path, similarity, centrality. For route optimization and supply chain, MIS is a big one. Maximum minimum spanning tree, and centrality. For entity resolution, we use similarity algorithms as well as PageRank, finding the most important influencers within a given community. So this means that you're traversing every node in the graph along every edge, and then you find out which is the most influential node in that community. Finally, we use feature extraction for machine learning, so similarity, community detection, ranking, and shortest path. So we're about to release a new product called the Graph Data Science Library in our machine learning workbench. We actually have some 50 different algorithms that we're integrating with the Graph plus ML workbench, and it's going to be open source. We're moving into a world where we're thinking, we foresee that banks and other financial services institutions are going to have to publish their algorithms as part of their regulatory filings. And we want to be able to make that easy and powerful and very, very compelling way to do that. So summary is we do deep link analytics, we can handle scale, and the compute programmability is the most important part of what we do to work together with AMD. Okay, over to you.
Thank you, Michael. Thank you. So I'm going to talk to you about how AMD Alveo PCI accelerator card can be put to use and how we have actually worked very closely with TigerGraph to provide a seamless integration to help you achieve massive acceleration for your graph processing. So this picture that you see there, it shows our PCI card, that's U55C. It has an FPGA on it. The right side shows the building block of FPGA. If you're not already familiar with FPGA, I'll have a quick sort of explanation. So FPGA has lots of ALUs. In this case, like around 10,000. Then it has the digital circuit building blocks, flip-flops, combinatorial logic building using lookup tables, like those are memory cells, essentially. There is interconnect running all over the fabric. And then all those interconnects can be, connections can be made just by putting a bit 1 in an SRAM cell that drives a pass transistor. So basically, you put 1, then the transistor turns on and the connection is made. It's as simple as that, right? So what happens is the way you use this is you write your algorithm in C++, and then there is a compiler toolchain called Vitis. It analyzes your algorithm, and it synthesizes a custom digital circuit for your algorithm. So that's very different from CPU and GPU, which are fixed functions. You have already built the hardware circuit, and then your algorithm is converted to a series of instructions or assembly instructions. Right? So that's why CPUs and GPUs are very good at like handling general problems, but they can't be as efficient. They can't be as fast. Whereas FPGAs, if you can take a certain set of problems and create an implementation for that and provide a library, you can get massive acceleration. So in addition to the compute power, we also provide 200 gigabit per second of network connectivity. So if your data size is very large, as I'll explain later, you can put lots of these cards together, connect them using any kind of network you like, let's say Ethernet. And then you can have this large-scale problem computing at scale with very minimal overhead. Yeah. And then, of course, this is 100 gigabit per second PCI. So whatever data you want to offload to the card, that can go over PCI. There is also 16 gigabyte of high bandwidth memory with 32 parallel channels and 460 gigabyte per second of bandwidth. So that allows you to build custom data paths, as I'll explain in the next slide. As I was explaining, the region Alveo card, which has FPGA on it, is so fast, is number one, you can do function level pipeline. You know, in the CPUs and GPUs, they do instruction level pipeline, and they build some fixed pipeline. There'll be 5 deep or 6 deep, right? Here, there is no limit how deep you can build because you got the whole scratch pad, right? Depending on the algorithm, we can figure out what's the best, and we can build that pipeline. So in this particular picture on the left side, you see function 1, it's processing certain data. And now the data flows from function 1 to, say, function 2. Then the function 1 can start taking new set of data. It doesn't have to wait for data to get through all the chain of functions. So that gives you performance. If you go to the bottom, I show now you can create multiple equivalent of cores, like for your algorithms, like custom code for your algorithm. So you can put lots of them together. Other thing you can do in FPGA, you can have a non-von Neumann implementation. For example, if you are trying to find top 100 elements, yeah, so any CPU or GPU will take at least n log n, right? In here, what you can do is you can put a set of combinatorial logic. So every clock cycle as data flows, the bits and so data can be swapped so that it stays sorted. So at the end of your compute, you just look at that and you already see it sorted, right? So that's that combination of having these pipeline blocks and custom efficient circuit sort of multiplies to give you a very good acceleration. Next, you can create a custom network because it has QSFP port, and so it doesn't have to be particular Ether. You can do Rocky V2. You can do InfiniBand, whatever you want to do. You can implement, because it's a fabric, you can implement the logic to have the connectivity. And last but not least, combination of the memory channels and the SRAM that allows you to create a custom data movement. So you can have a stall-free data access. For example, you can lay out constants and variables in a certain way in the memory, and then you can make sure that every clock cycle, hardware always gets the data, so it's never stalled, and that's what gives you compute efficiency. What we have done to make it easy for this power of compute to be available to the users, we have worked very closely with TigerGraph, and we have done an integration which is almost like drop-in replacement. So today, let's say you are using G-SQL, or you're using Jupyter Notebook or a web client using Python. You don't have to make any changes in your code. We have used the UDF functionality that TigerGraph has, user-defined functions, that's in C++, that talks to our runtime. And then we have also provided a stub for G-SQL and in Python, so that you can stay in your favorite environment and just leverage the power of acceleration without having to worry about it.
And just a quick note on this logical block diagram we're looking at. When you look in the upper left, we talk about a graph query language. So, sorry, yes. So when you look at the upper left, when G-SQL, graph structure query language, is how we think about asking questions of the graph. Now, what we're also doing with adding this UDF function, the user-defined function, is we're able to plug in other analytic frameworks to be able to ask questions even faster. So the point is that we're able to do this on CPU in the upper left, and we're able to do it on FPGA on the upper right.
Yeah, thank you, Michael. Since TigerGraph is written in C++, there is almost zero overhead in sort of going from TigerGraph processing engine to Alveo. And for each algorithm, you already have these bit streams, which we call XCL bin created, so like a library. So you can swap the bit stream depending upon what algorithm you want to load. And the swapping takes a few seconds. So I wanted to show an example of how a complex graph processing algorithm, such as Maximal independence set that Michael talked about, is accelerated on FPGA and what sort of acceleration we get. We are working with several customers to put this in production. So this graph shows you have this travel plans, or the trips that you need to make. So let's say, for example, you are Tesla and you want to deliver new cars. to your customers. A lot of people have ordered. You have these work orders, so you build a graph, and then you realize that I have limited number of trucks and limited number of drivers. So what you do is each of these trips that you need to make, if there is anything shared between the trip, you put an edge. Yeah, it's sort of like a conflict graph. And then you run this algorithm, maximal independent set, whose job is to find the biggest set of nodes who do not share a direct edge. So once you found that, you can make all those trips in parallel because there's no conflict. So you can dispatch your trucks, so many trucks. So your goal is to find the biggest maximal set in the shortest amount of time. And once you have found that, in this particular one, all the red ones, you dispatch those trucks, and then you mark those nodes as deleted. And then you again go and run the MIS on it. You find the next set of dispatch, and you keep doing that iteratively. So you can see this is a very compute-intensive problem, and if done on CPU, it can take days. So this graph shows how the acceleration compares on Alveo, with respect to compared to CPU. So the gray one is the Alveo one, and the CPU one is the AMD 128 core CPU. You can see that in every iteration, we find bigger MIS and faster, like 260x faster, right? So what we found that when we ran, there was a 75,000 node graph, right? Vertex graph. That was a travel point from a real customer we got. That when we ran on CPU, through TigerGraph, of course, that took like 5 days. 5 days to actually get all the dispatches made and all the MIS found in each iteration, right? And Alveo did that in 17 minutes, right? So that's the kind of power we have. And good part is that we are also making this acceleration available on cloud. So AWS has a F1 instance, which has Alveo acceleration. Azure has an NP instance, which has Alveo acceleration. Yeah.
And I think that, the important thing about this, what's important here is that we're noting that we're actually making supply chains more resilient, more responsive, and we're saving a ton of carbon, literally, by taking this approach. And we're able to actually deliver breakthrough business value to shipping companies, to logistics companies, train companies, truck companies, and we're able to actually deliver this solution in much more closer to real time than the long batch process that would be CPU bound. This is the equivalent of a computer science grand challenge in the real world, with depots and with parts and pieces and all the rest. And we're able to actually help customers solve billion-dollar problems in this manner.
Yeah, thank you. Another example is we are doing for a large bank, US bank. They have this problem of extracting features from their graph of customers, credit card number, account number, personally identifiable information such as social security number. Their problem is that as Michael was talking earlier, there could be too many applications coming from the same set of IDs, which increases the risk of default. So they want to find how many paths exist between the two set of IDs. Let's say an email and a social security number. So from email, you go to all the applications linked with that email. From that application, you go to all the other PIIs. From there, you go to other applications. And then eventually, you're looking for that end pair ID, let's say phone number, right? So you can see this is like explodes in compute. The moment you go beyond 2 hop, it just explodes in compute, right? You're talking like days of running on CPU. So the way what we are doing this with this bank is we are going to have 135 Alveo cards. And these Alveo cards are networked using Ethernet. And these kernels they look at a partition of the graph. They start in parallel. Whatever they cannot find in their partition, they queue it up for the other guy, and the other guy processes and return it back. And ultimately, everything aggregates on each card, and that's uploaded to CPU, and result is presented in TigerGraph. So next, I want to show that what we have found.
Sorry. This bank is using TigerGraph.
Yes. This bank is using TigerGraph, and
they're saving tens of billions of dollars because they're avoiding synthetic identity fraud.
So I wanted to show like some really heavyweight algorithms that we have built acceleration for in TigerGraph, and these are like drop-in replacement. So you can go to, let's say, F1, install TigerGraph, and install our plugin by just running install.sh, and then you can start seeing the acceleration, right? So you can see we get 50x or more acceleration in all of these very compute-intensive graphs, algorithms. But in some of those cases, we also get a better QR, right? We get bigger MIS, or for Louvain, we get a better Q-score, right? But that's not end of the story. In some cases, in fact, it reduces the system memory requirement for CPU. So you don't need to buy as much RAM, right? That's a useful saving. And what we have started to do is that we started to do graph ML libraries as well. For example, FastRP is the embedding creation algorithm. So we're starting to accelerate that. And we're going to do soon the graph neural network. And we are seeing like the 50x plus acceleration on that. So the idea is that for all graph and all graph ML related algorithms, just have a drop-in replacement so that you can take advantage of this acceleration. AMD is running a proof of value program. So if any of you have a computationally intensive challenge where you're not able to do it with CPU, it's not fast enough, you want to save cost, save power, please reach out to Vinay Singh, and we can just engage with you and help you. To conclude, Michael, maybe you can.
Sure. So again, what we're talking about in terms of problem set is that we have a highly sparse matrix approach to things, but once we start to see density increase, it becomes increasingly powerful to use FPGAs. It's a full graph traversal. We're touching every node, every edge, and in parallel in very powerful ways. CPUs end up being serialized and narrow. FPGAs end up being wide and parallelized. And so the summary is that we see FPGAs as being the future home for the most powerful graph analytics, solving the great challenges that our customers are up against. Thank you very much, everyone. If there are any questions, please raise your hand or let me know online.
So is this like a cluster off to the side that's storing the?
No, it's inside. It's in graph.
Thank you. Thank you very much. We're at time, so we'll keep the conversation on Slack and in the at the break. So thank you very much.
Thank you very much.